Hi, I'm Jordan Snyder, and today I want to talk to you about fitting a curve to data. And we're going to talk about this both from a theoretical point of view and in code using Matlab. So, just to set up the problem, we suppose that we have some data. This is a set of x and y measurements, xi, yi, where I runs from 1 up to n, where n is going to be our number of measurements. So these are just some scalar variables that we suppose are related in some way. So what we would like to do is to learn a relationship between x and y. And the way we do that is by supposing a model. We suppose that the y variables can be expressed as some function of the corresponding x variable plus noise. Okay. So we suppose that there is some underlying relationship, but that what we measure may in fact be corrupted with noise. So our task is to learn the function f that expresses a relationship between x and y. So there are infinitely many functions, there are infinitely many classes of functions, so we have to specify a little bit what we actually mean when we talk about what function we're looking for. So one possibility that I'll run with for this example is using a polynomial model. So we could suppose that yi can be expressed as a polynomial function of x. And a polynomial can be written in terms of its coefficients. So we will have a constant term, a0, plus a linear term, a1, plus a quadratic term, a2, all the way up to am xi to the m. So m is going to be the what I call the maximum degree of my polynomial. So if we suppose that the relationship between x and y can be approximately written as a polynomial, then our task of finding a function that relates x and y is reduced to finding these coefficients, aj. So we have now our unknowns are a0, a1, all the way up to am. Okay, so because we restrict our attention to a particular function family, this becomes a problem of finding just numbers. Now, how do we find these numbers? Well, a first step towards that is to notice that the right-hand side here depends linearly on these coefficients. So that should suggest to us that we can write this as a system of linear equations. And we can do just that. So let's set that up. On the left-hand side, we're going to have a vector containing our y's. So we'll have y1, y2, going down to yn. This is our y data vector. And we suppose that this is approximately equal to, approximately because remember, there's noise. Then there's going to be some matrix times our vector of unknown coefficients. So a0, a1, all the way down to am. Okay. So what should we fill in the entries of this matrix? Let's just consider the first row. So y1, according to this expression, should be equal to a0 plus a1 x1 plus a2 x1 squared, and so on, up to am x1 to the m. So we can fill that in column by column here. In this column, we should have number 1. That's 1 times a0 plus x1 times a1 plus, and so on, plus at the end x1 to the m. So as you go to the right along a row, the power of x will increase. The same is true for the next row, except for now we look at the second data point instead of the first. So we still have 1 in the first column, then x2, and then higher powers of x2 up to x2 to the m. And this continues all the way down until we reach our last row, which still has a 1, then xn, then xn to the power m. Okay. So what we have is the y data is equal to a matrix that depends on the x data times an unknown coefficient of a's. So we can write this as y vector is approximately equal to a matrix that depends on the x vector times the a vector. Now, one thing you can notice about this linear system is that typically our number of measurements is going to be larger than our number of terms. So if you think about a polynomial, a reasonable degree polynomial might be 2, 3, 4, but hopefully you would have hundreds, thousands, possibly even millions of measurements. So you have many, many rows, but few columns. So in linear algebra terms, this is an overdetermined system. Meaning we don't have enough freedom to choose these a coefficients in general to exactly satisfy every single row of this equation. So because of that, we need to look for an approximate solution. The most commonly used sense of an approximate solution is called least squares. So we'll look for the minimum over choices of a vector of the difference between these two sides of the equation. So the norm difference between y and the matrix of x times a. And typically it's left as a square because if you minimize the square of the norm, you also minimize the norm. Okay, so this is the mathematical framework that we're going to use to set up our curve fitting problem. And now I'm going to turn to this Matlab code and show you how this works in practice. So, for the purposes of this example, we need some data. So what I'm going to do is just generate some data. So to do that, I need to specify how many data points I want. So here I'm saying n is equal to 100, so I want 100 data points. And then I need x's and y's. Now, in this modeling framework, I'm supposing that the y's can be written as a function of the x's plus some noise. So for that reason, I'm going to just generate the x's directly from a uniform distribution, and then create the y's via applying a function to those x's. So this is what I'm doing here. I'm creating the x data as 2 times a random vector. Now, in Matlab, the rand command takes 2 shape arguments. This is the number of rows and the number of columns. This is an n by 1 matrix, otherwise known as a n-length column vector. And by default, this gives random numbers from 0 to 1, uniformly distributed. And I would like to change that just because I feel like it, and so what I'm doing is multiplying by 2 on this vector. So x data contains uniformly distributed random numbers between 0 and 2. So now I have to create some y data. So to do that, I'm going to apply a function to the x's, and that function is being defined in this line, true fun. This is a MATLAB notation for creating a function in one line. So I can just say this is a function that takes in an argument called x and outputs the square of that x minus twice x plus 1. So my true function is x squared minus 2x plus 1. Now this is sort of setting myself up for success when I'm fitting a polynomial model because the true relationship in the data is actually a polynomial. In general, you don't have this condition, so you in general can't expect perfect fitting for your data. But in this case, we can have higher hopes that we're actually going to get a model out that's close to the true model. So, so this is my polynomial function, and then I can just apply it to the x data to get what I'm calling y true, sort of the true f of x without noise. And then finally, to create the y data, I need to add noise. To do that, I'm going to specify a noise level. In this case, I'm choosing 0.2. And then with that noise level, I'm creating a noise vector by multiplying the noise level by normally distributed random numbers in a column vector of length n. So this is the same shape as x data and y true. And then I finally get y data by taking the true y values and adding noise. Okay. So we've got x data and y data. So what I'd like to do now is just plot the data. And this is a good step to do anytime you have some data that you want to fit. Just plot it and see just visually what you can understand about it. So I've just run this code. And this is a Matlab live script, by the way, so this works similarly to Jupyter Notebook if you've ever seen that. So I have code here, and then it's outputting figures in line here. Okay, so on the horizontal axis I have x, and the vertical axis I have y. So you can kind of see this sort of parabola shape that I built into the data using the polynomial function, but there's quite a bit of noise. So our task with curve fitting is to basically draw a curve through the center of this noisy cloud of data. And now we're going to actually fit the model. Okay, so to fit the model, we need to set up this system of equations. So we need to create this matrix. But before we create that matrix, we need to actually specify how many columns it has. In other words, we need to pick the maximum degree of polynomial that we're going to consider. For this demonstration, I'm going to pick m equals 3, so I'm going to allow up to third order or cubic polynomials. So with that, I have m equals 3. Now I need to create this matrix. The way I'm going to do that is I'm going to start with a matrix of all zeros of the appropriate shape. Now, what is the appropriate shape? I can tell that I have n columns, so one column for each measurement, and the number of, one row for each measurement, I should say. The number of columns, the columns start at the 0th power, and then we have the first, second, and so on up to the mth. So we have m plus 1 columns. So that's why I create a matrix of zeros with n rows and m plus 1 columns. Then, so I have a bunch of zeros, I need to actually fill these in with the numbers that should be inside that matrix. And I can do that in two ways, at least two ways. So the first way you might think of is just sort of walking along through every single entry of this matrix and filling it in with the appropriate quantity. So that's what I'm doing here. This is a nested for loop. The outer loop, I, is running through the rows going from 1 to n. And then the columns are running from 0 to m. So what do I do at the ij step? I'm setting the ith row and the j plus 1th column, again because MATLAB is 1 indexed. So when m equals 0, I want to look in the 1 column and so on. I set that quantity to the ith data point raised to the jth power. Okay, so the data point number increases down the rows, and the power increases across as we step through columns. Okay, so this nested for loop is a perfectly valid way to create this matrix. Another way is to notice that when I make these columns, I'm really just taking a whole vector and applying the same computation to it, namely I'm raising it to a power. So what I can do is actually loop through the columns. So here I'm just taking 4 steps rather than doing 100 steps times 4 steps. So here I'm just looping through the columns that I need to create, and then I'm creating each column. So in MATLAB, you put a colon. Putting a colon means consider all indices in that slot. So this is saying every row in the j plus 1 column, and you set it to this entire x data vector raised to the appropriate power. And this dot indicates element-wise operation. Okay, so these are perfectly equivalent. They create the exact same matrix, but this one is going to generally run faster because writing out loops like this, it's typically a slow operation. So this is a good habit to get into when you're able to do something in this is called a vectorized way, where you take an entire vector at once and operate on it, then you can typically see really good performance gains. It's a good habit to get into. Okay, so we have our matrix, we have our data vector. The last thing to do is actually solve this minimization problem, this least squares problem. So the way to do that in Matlab, because Matlab is so specialized around linear algebra, there's a single character way to do this, and it's the backslash. So we're not going to cover sort of the internals of actually how you solve this least squares problem, but just know that in MATLAB this is, for most cases, a solved problem, and it's the way you call it is with the backslash. So what do we actually do here? So we have two known quantities, m and y, and the single unknown quantity is a. So the notation for this in MATLAB is matrix backslash data vector. So m backslash y gives me a hat, which is the minimizer of this problem. Okay, hat meaning the optimal value. So I believe this code is already run, and so it's printed out the a hat vector. So this is the best fit coefficient vector for this least squares problem. And already we can go ahead and interpret this in terms of a polynomial model. So these are exactly coefficients that I should put in a polynomial. So this is saying that my best fit model is 0.95 minus 1.67x plus 0.46 x squared plus 0.2x cubed. Okay, so I happen to know that there's no cube term in the true model, but in this case we found a best fit model with a non-zero cubic term. What we can also do is actually visualize the results. So what I want to do now is plot the x's against the predicted y values. So we can view this this model that we fit as a way to predict an estimate of what y could be. So if we have an unknown, if we measure an x but we don't measure a y, this model could give us a way to predict what y value we might get if we were to measure it. Now, what actually is that prediction? That prediction is just going to be this matrix vector product here. So this is the truth, this is the actual data, and it's approximately equal to this model prediction. So this is what I'm going to be calling the model prediction. Okay, so that's what I'm going to plot right now. Let's analyze the results. So I'm getting y prediction is equal to the matrix vector product of m times a hat. Now again, because MATLAB is so specialized for linear algebra, when you have two matrix objects and put a star between them, MATLAB assumes that you're talking about the matrix vector product. So that is correct in this case, so we just get y pred is equal to m times a. And then we're going to plot everything. So what we've got here is the model predictions that are going to be cyan x's. Then we're going to put the data, just the same as we plotted before. And then we're going to get the sort of true relationship. Now this is something that doesn't exist in a general curve fitting setting because you just have data. But in this case we do know the true relationship, so I want to plot that just so we can see how well this curve fitting procedure has done at uncovering that. So to do that, I need to do a couple things. So I want to draw a line through corresponding to that function. So to do that, I actually need to sort the x values because these x data values are not in any order, they're just random. So what I'm doing here is I'm sorting the x data, and when you sort in MATLAB, it gives you the sorted array. So that's the first output. And then the next output is IDX, so it's an index object that tells you the ordering. So it gives you the order that you have to put the X data in order to sort it. So what this allows us to do is to sort the corresponding Y true values. because these also were not sorted. So when I do this, this gives me sorted x and y values that I can draw a smooth line through. So let's go ahead and see what this plot looks like. So here we go. So the yellow line is the true function. That's y equals x squared minus 2x plus 1. And then the white points are our data. So again, we see this sort of noisy relationship around the parabola. And then in the cyan x's, we see the model predictions. So in a way, this looks like sort of the data cloud with noise subtracted. And you can see that we've actually done pretty well in terms of fitting to the true model. So just to recap, we've talked about what it means to take data and fit a model to it. In this case, we talked about polynomial models, in which case the fitting procedure amounts to learning coefficients. And these coefficients can be expressed as the solution to the least squares problem. And in Matlab, we can set up the matrix and solve the matrix and then plot the results. So thank you a lot for watching, and I'll see you next time.